Hey, hey, it's the video for the makeup practice exam. Done. In this first question, we're looking to see which of the following compounds contains both ionic and covalent bonding. So we're looking for a salt that has some sort of polyatomic ion in it. And it happens to be this one right here, ammonium bromide. So if we look at the structure of ammonium bromide, this is an ammonium salt, where we've got an ammonium, NH4+, it's got its positive charge on it, and a bromide anion. Oh! So we have the covalent bonds found inside of our polyatomic ion with the nitrogen-hydrogen bonds. And then we also have this interaction between the positive charge and the negative charge that gives us our ionic bonding. This question is asking us about silver. So cyanide is often used to leach precious metals. And here, particularly, we're looking at a silver +1 cation, which is Ag+. So anytime you want to find the electron configuration of a cation, always start by writing out the electron configuration of the neutral element first. So, for silver, it's got a krypton core, and then it's going to be 5s1, a little bit of a twist there, 4d10. So recall that the precious earth metals, things in the 9th column of the transition metal, like for example copper, silver, gold, in order to get more stability for their neutral atom, the D subshell borrows an electron from the S subshell. So we have this fully filled D subshell, which confers some extra stability to neutral silver. Now, the question is actually asking for the electron configuration of silver plus. So silver plus will still have that krypton core, but we need to remove one electron to give it a +1 charge. And remember, when removing, always remove from the furthest out shell in terms of the principal quantum number first. So we're going to actually remove that electron. The 5s1 electron is going to be easier to remove than the d electrons. So always start by looking at the principal quantum number. The higher the principal quantum number, the easier that electron is to remove. So then this just ends up being 4d10. Krypton core 4d10 for the win. This question is about the objectively outstanding color salmon. It's a mixture of different wavelengths, and one of those wavelengths is 635 nanometers, and we want to know what the energy of a photon is with this wavelength. So recall, if we want to relate the energy of photons to the wavelength, we can use the following equation. Energy is equal to Planck's constant times the speed of light, hc, over lambda, the wavelength. Now there's just two quick caveats to insert into here. Recall that the energy needs to be in joules per photon in this equation. Also, recall that our wavelength needs to be in meters. As long as you keep that in mind, you'll be good to go. So our energy is equal to Planck's constant, 6.63 times 10 to the negative 34th joules seconds, times the speed of light, which is 3.0 times 10 to the 8th meters per second. And then we're going to divide all of this by these 635 nanometers, and recall that a nanometer, the prefix nano means times 10 to the negative 9th. So it's going to be 635 times 10 to the negative 9th meters. And when we do, we'll end up getting our energy in one photon. And our units cancel out, and we get 3.13 times 10 to the negative 19th joules. And that is not a lot of energy, but just recall, this is the amount of energy in one measly photon, one measly particle of light. When you have a mole of photons, it ends up being considerably more, on the order of kilojoules per mole. This question is, to quote Schmiegel, a little bit tricksy. We're trying to find the root mean square speed of 2 moles of hydrogen gas, take up 1.5 liters at a pressure of 0.75 atmospheres. Okay, so this is actually going to be a two-part question. We're trying to find the root mean square speed, right? So our equation for that is root mean square speed is equal to the square root of 3 times the gas constant R times the temperature times the molar mass. So 3 is a constant, we have that. R is a constant, we have that. The molar mass of hydrogen we can figure out by looking at the periodic table It's the temperature here that is the unknown. So we need to first figure out the temperature before we can proceed using this equation. And I don't mean to alarm you, but if we look at what we're given here, we have moles, cool. We have a volume, V. We have a pressure. So we're trying to relate moles, volume, pressure, and temperature. Is there some sort of equation that relates moles, volume, pressure, and temperature? That's right. When in doubt, nerd it out. Our pressure is 0.75 atmospheres. Our volume is 1.5 liters. Our N is 2 moles. We have 2 moles of gas here. Our gas constant, since our pressure is in atmospheres, is going to be 0.08206 liters atmospheres per mole Kelvin. And then finally our temperature, T, well, that's what we're solving for. So, to solve for that, we're going to divide both sides by the 2 moles times the 0.08206 liters atmospheres per mole Kelvin. And when we do, liters and atmospheres and moles all cancel out. And this whole thing cancels out over here. And Kelvin's in the denominator of the denominator, so it jumps up to the numerator, and we get 6.85 Kelvin. It's a pretty low temperature, but let's roll with it. Now we have everything we need to figure out our root mean square speed. So it's going to be equal to the square root of 3 times our gas constant R. Now remember, whenever you're using this equation, we're going to use the version of the gas constant that relates energy and temperature. 8.314 joules per mole Kelvin. And then our temperature, well, we're going to plug in that 6.85 Kelvin that we got before. And then we'll divide this all by the molar mass. Remember, the molar mass, whenever you're dealing with energy, we always want to deal with kilograms. So for H2, it's 2 grams per mole, which means we'll divide that by 1,000. We'll get 0.002 kilograms per mole. Now we have everything we need to get the root mean square speed. And so we end up getting here that the root mean square speed ends up being 290 meters per second, which is this answer right here. And if you're curious where those units come from, a joule is equal to a kilogram meter squared over second squared. And so if we were to plug this in to our equation up here, so we would get kilograms canceling out, the moles already cancels out, the Kelvin already cancels out, so we're left with our units end up being the square root of meters squared over second squared, which is just meters per second. This next question is about something that many of us can relate to. It is about road salt. So when it gets really cold, we can use salts to help lower the freezing point of ice, which lets it melt at a lower temperature so that we don't have ice all over our sidewalks. So, in this particular problem, we're given a 1 kilogram bag of road salt, and we want to find out how many ions are present when this is dissolved into water. Okay, let's do it. So 1 kilogram is equal to 1,000 grams, and our road salt is magnesium chloride. And fun fact, a lot of it is derived from the salt of the Great Salt Lake. Okay, so now let's do some calculations. So to convert to the universal currency of chemistry, the mole, we need to use the molar mass, so there are 95.2 grams of magnesium chloride for every 1 mole of magnesium chloride, which ends up giving us 10.5 moles of magnesium chloride. Okay, so now, is that what we're looking for? We're looking for the moles of magnesium chloride. We're looking for the number of ions present. So, first of all, what is magnesium chloride? Well, it's a strong electrolyte, so it will dissociate completely into ions in this aqueous solution. So, the equation will look like this. So, for every 1 mole of magnesium chloride, we actually get 1 plus 2, 3 moles of ions. Okay, cool. Now let's do this calculation. So, for every 1 mole of magnesium chloride, there are 3 moles of ions. And for every mole of ions, there's 6.02 times 10 to the 23rd, Avogadro's number of ions, which gives us our answer, which is 1.90 times 10 to the 25th ions. This next question tasks us with figuring out which of these is predicted to have the lowest melting point. So melting points of salts comes down to two things. First and foremost is the charge. The greater the magnitude of charge, the more tightly these ions are going to be held together, a la their electrostatic potential energy. So the greater the magnitude of charge, the greater the lattice energy is, the more heat it's going to take to melt these apart. The next thing that we look at is size. So charge is the most important factor, and then size is next, and we'll get to that in just a moment. First, let's analyze the charge. Most of these salts are +1, -1 salts. So we have a group 1 metal and a group 7 nonmetal. So like for example, lithium chloride. Lithium has a charge of +1 by virtue of being a group 1 metal. When it's in a salt, chloride in a salt will have a -1 charge. Okay? Same thing with potassium iodide here, +1, -1 salt. Same thing with sodium bromide, +1, -1 salt. Same thing with lithium fluoride, +1, -1 salt. The only one that's really different here is the strontium sulfide. Strontium sulfide, so strontium is in group 2, so it has a charge of +2 when it's found in a salt. Sulfur is in group 6, so in order to get its octet, it needs to gain 2 electrons, so it has a -2 charge when in a salt. So because this one has a +2 charge and a -2 charge, this one is going to actually have a melting point that's about 3 or 4 times greater than the other salts here, because this +2, -2, this magnitude of charge means basically there's 4 times as much lattice energy as the other ones. So we're going to eliminate this answer choice. Now, we've looked at the first trend. The second trend to find the one with the lowest melting point is size. So recall for size, we can use the snowman rule. And what that means is if you're comparing elements within a group as you're going down, we can draw a snowman next to the periodic table. Just like a snowman, elements get larger as you go down the periodic table, because there are more shells. So it adds more layers to the proverbial parfait of an atom or ion. So when comparing the group 1 elements in this particular problem, lithium is in the second period of the periodic table. Below it is sodium, and below sodium is potassium. So potassium is the largest of these elements, so it's going to be the largest cation here. We can do the same thing with the halogens, and it turns out that iodide is the largest of the halogens that are present here. So what that means is, in choice B, we're looking at a +1, -1 charge, and we're also looking at very big ions. The larger the ion, the less the lattice energy is, because the point charges can't get as close to each other, they're just not as attracted. So the greater the size, that means a decrease in the melting point, generally speaking. So the one that's going to win here is potassium iodide. It's going to have the lowest melting point. To put this another way, because of their smaller size, small ions can get really, really close to their anion counterpart, whereas something like potassium iodide, which is significantly larger, because there's more shells separating them, these charges can't get as close to each other. And so, as a result, we don't have as stark of a attraction there. This question asks us to find the total pressure in a mixture of gases where we know that the helium is 0.25 for the mole fraction. We're also told that there's 8 grams of it, that the volume of the flask is 800 milliliters, and that the temperature is 50 degrees Celsius. Wait a minute. Oh no, it's happening again! We've got mass, we've got volume, we've got temperature. We're trying to find pressure. When in doubt, piv nerd it out. So we need to find the number of moles of helium. A la the periodic table, helium is 4 grams per mole. So that means that we've got a cool 2 moles of our helium present in the sample. Also recall that volume needs to be in liters and temperature needs to be in Kelvin. So the temperature is going to be the 50 degrees Celsius plus 273 to turn it into Kelvin, which gives us 323 Kelvin. Then finally, we're told that it's 800 milliliters. If we divide by 1,000, we end up getting 0.800 liters. That's going to be our volume. Okay, now we have everything we need to solve for the pressure caused from helium. Let's do it. So we're solving for the partial pressure from helium. Our volume here again is 0.800 liters. So we're going to set that equal to our number of moles. So this is equal to N. We have 2 moles of helium times our gas constant R, which is 0.08206 liters atmospheres per mole Kelvin, and then finally our temperature is 323 Kelvin. So we'll divide both sides by the 0.8 liters, and we'll end up getting the partial pressure of helium, which is 66.3 atmospheres. So that's the partial pressure due to helium, because we're only taking into consideration the moles of helium in this calculation. But the problem is actually asking for the total pressure. So now what we need to do is use the fact that helium is only 25% of this entire mixture, which means it's only exerting 25% of the total pressure. So now we can calculate to find the total pressure by using this relationship. The partial pressure of a given gas, in this case helium, is equal to the mole fraction of said gas, again we're using helium, times the total pressure. So let's plug in our values and see what we get. So we get that 66.3 atmospheres is equal to our mole fraction, 0.25, times the total pressure. So we're going to divide both sides by 0.25. Basically this means that the total pressure is going to be 4 times as great because there's 4 times as much gas in there as compared to just helium. And we'll end up getting 265 atmospheres for the total pressure. This problem is a little bit of a twofer. We have to do 2 things here. First, we need to figure out, we're trying to find the largest atomic or ionic radius here. So first we need to find out what electron clouds each of these have around them. They all have noble gas electron configuration. So let's put these in like terms with each other. For example, well, krypton is a noble gas, and so krypton has, appropriately enough, krypton's electron configuration. Cool. Bromide actually also has krypton's electron configuration. Lithium plus has helium's electron configuration. Selenium 2-, so selenium 2- also going to have krypton's electron configuration. And then finally we have a pirate's favorite noble gas, argon, which has argon's electron configuration. So using the snowman rule that we used on a previous slide, if we're comparing all these noble gas configurations, the ones that are the largest are the ones that have krypton's electron configuration. So we've narrowed it down to either krypton, bromide, or selenium. They all have the same electron cloud around them. What is different is what's in the nucleus. So when comparing the nuclei of each of these, we have to look at the number of protons. So we have 36 protons, we've got 35 protons, and we've got 34 protons. These are the number of protons in each of these, so they all have the same exact electron cloud around them. But which one of these is going to pull in the electron cloud the closest to the nucleus? Well, the more protons there are, the more the electron cloud is going to be attracted to the nucleus. So of these 3, this one is going to be smaller than the other 2. The one that's going to be the largest of these 3 is going to be the one that has the fewest number of protons. So fewer protons means, if you're comparing isoelectronic series, if you're comparing elements that have the same electron cloud but differ in the number of protons, the fewer the protons, the larger it's going to be. So this is going to be our winner chicken dinner. And now we want to find mass percentage of oxygen in aspartic acid. First I'm going to count the carbons here. So remember, each point in our skeletal structure represents a carbon. So it looks like we've got 4 carbons here. So our formula is going to be C4. Let's do hydrogens next. So recall that skeletal structures assume that every carbon has its valence satisfied. And whatever we can't see, the bonds that we can't see, are taken up by hydrogen. So there's a hydrogen here and a hydrogen here. This carbon right here must have one hydrogen that we're not seeing on there, these sneaky hydrogens. And other than that, all of our other carbons have 4 bonds, so they're good to go. So now there's a total of 1, 2, 3, 4, 5, 6, 7 hydrogens. Up next, we'll count the oxygens. There's 1, 2, 3, 4 of those, so O4. And that leaves us with just nitrogen, which if we look at our structure, there's just this one lone nitrogen here. And here's our formula. Okay, so we're specifically trying to find the percent mass composition of oxygen. So what we need to do is find out the mass of oxygen in this molecule, and then we need to divide it by the total mass and multiply by 100. So oxygen is 16 grams per mole, and there's 4 of them here. So that ends up giving us that there's 64 grams of oxygen for every mole of this molecule. Now we're going to do the same thing for all these other elements. Carbon is 12 grams per mole, and there's 4 of them. Hydrogen is 1 gram per mole, and there's 7 of them. Nitrogen is 14 grams per mole, and there's 1 of them. So we're going to add all these up and making sure that we're including the oxygen as well. We end up getting that aspartic acid is 133 grams per mole. So the percent mass for oxygen is going to be equal to the 64 grams per mole of oxygen divided by the 133 grams per mole of aspartic acid. And since it's a percentage, we're going to do this all times 100, and we'll end up getting 48.1%. This question wants to know which of these represents the process of the electron affinity of fluorine. So electron affinity is what happens if you're looking at a given element, X, in its neutral state, and it's literally the affinity, it's how much it wants to gain an electron. So it's the reaction from taking a neutral gaseous atom, adding in an electron, and then forming the 1- anion. So we're looking for this. I just used generic gas X. We're just specifically looking at fluorine. So if we look at these, which of these corresponds to that reaction? It is choice D. In this problem, we're trying to find the molecular formula of paraphenylenediamine. All right. And we're given some mass percentages here, and we need to translate this into an actual molecular formula. So whenever you're looking at a molecular formula and you're given mass percentages, it's easiest just to assume that you have 100 grams of this substance to find the empirical formula. So what I mean by that is, if it's 66.7% carbon, okay, so if it's 66.7% carbon and we have 100 grams of a sample, it would be 66.7 grams of carbon. Okay? So we're going to use the same logic then. If we have 100 grams total and it's 25.9% nitrogen, that would be 25.9 grams of nitrogen. Because the formula, it's arbitrary how much you have. It doesn't matter if you have 100 grams of it or 1 billion grams of it, it's still going to have the same formula. Finally, whatever's left over here is going to be hydrogen. So if we add up the 66.7 grams of carbon plus the 25.9 grams of carbon, we get what seems to be about, that ends up being 92.6 grams of carbon and nitrogen. Whatever's left over is hydrogen. So we'll subtract that from 100 and we end up getting 7.4 grams of hydrogen. So this is the relative amount, mass-wise, of all of these different elements in this compound. But we need to use the universal currency of chemistry, the mole. So that's what we're going to do. Carbon is 12 grams for every 1 mole. Nitrogen is 14 grams per mole. And then finally, hydrogen is a nice round, there's 1 gram of hydrogen for every 1 mole of hydrogen. So let's see what we end up getting. So we end up getting 5.56 mole of carbon. Oops, I should have labeled that. 1.85 mole of nitrogen and 7.4 mole of hydrogen. Cool. So now in order to make these numbers a little bit more user-friendly, we're going to divide by the smallest value. This will give us at least one whole number coefficient we can work with. So the nitrogen is the smallest, it's 1.85. And when we do, we'll end up getting a ratio of 3 carbons to 1 nitrogen to 4 hydrogens. So this is our empirical formula. Empirical formula. So it's C4N1 and, oh no, sorry. C3, 1 nitrogen, and 4 hydrogens. So C3NH4. And this, again, is our empirical formula. Our empirical formula, if we add together, so 3 times 12 plus 14 plus 4 times 1 to account for all these different elements, this empirical formula that we have is 54 grams per mole. So the last thing we have to do is ask ourselves, does that match the actual molecular formula or the molecular weight that we're given? 108 grams per mole. The answer is no, it doesn't match. But we can see how many times it fits in to get that match. So we want to see how many times our empirical formula can fit into our molecular formula. So 108 grams per mole divided by 54 grams per mole, that equals 2. So what that means is we have to double all the coefficients in our empirical formula to get the molecular formula. So when we do, we'll end up getting that the actual molecular formula is C6N2H8, and that matches up. So our answer ends up being choice B. This question is asking which of the following will have the highest second ionization energy. So recall that we can play around with valence electrons. So you can add and remove valence electrons for a given atom. But we do not mess with core electrons. It takes too much energy to remove core electrons. So if you have something that's in group 1, for example, that first electron will come out very easily. In fact, more often than not, if we look at things like sodium and lithium and potassium, they are Na+, Li+, and K+, respectively. It's really easy for them to lose those electrons, but very difficult to take a second electron. So, since we're looking for the highest second ionization energy, what we're going to do is we're looking for something in group 1, where we can easily remove 1 electron, and then it's going to take a metric crap ton of energy to remove any more. So the ones that are in group 1 are potassium and cesium. The other ones, calcium and barium, are in group 2. They have 2 valence electrons that can be pretty easily removed. And then aluminum is in group 3, so it has 3 valence electrons that can be easily removed. Now between the 2 of them, we want to know which one is going to be more difficult to pull electrons away from. At this point, we need to consider size. So potassium is a lot smaller than cesium, which means its core electrons are closer to the nucleus than cesium. Cesium has more layers, so the second electron that we'd be trying to take out for cesium would be further away from the nucleus, not as attracted as potassium. So it's going to end up being potassium for the win here. Again, the reason why is because this is group 1, meaning a very high second ionization energy, and the reason why it beats out cesium is because it is smaller.